Moving on to look at another use of the t-distribution. We're going to be looking at the paired t-test. This is a way for you to measure the difference that may have occurred from some sort of treatment or impact or event. We might want to measure people's reaction times before and after they've consumed alcohol. We might want to measure people's heart rates before and after they've run a 5-kilometer race. We might want to measure the difference in someone's exam results before and after a 1-week intensive revision session. Two results we're measuring the difference between do need to be linked in some meaningful way. Usually it would be the same person that we are measuring their before and their after. It has to be linked, it has to be paired so that we're eliminating any natural variation that might happen. There's no point testing person A before their race and then testing person B's heart rate after the race. There may be some natural variation that's impacting any results we get. Okay, additionally, we are not going to assume that the data has come from a normal distribution, which you might have been anticipating. Instead, because we're looking at the differences, it's the differences that we map to a normal distribution. Additionally, for these differences, we're unlikely to know the variance. We can't know the variance. So with the population variance being unknown, that's one of the criteria to use the t-distribution. We also usually have a small sample, so that's the second criteria to use the t-distribution. And as I said, we're treating these differences between the pairs of data as if they follow a normal distribution. So the three criteria to make use of the t-distribution. Okay, so the test statistic T is going to be d bar, so the mean of the differences, minus mu d all over s over root n. Okay, so some things are similar, some things are slightly new. Be careful, a lot of students see this table, or they see a table like this, and it is set up exactly the same way as a Spearman's rank question would be set up. But just actually reading through the context of the question, we realize it's not a test of correlation, how well one variable, the reaction times before, is related to the other, the reaction times afterwards. It's about the differences in each individual person. It's about the change in their reaction times from person A before to person A afterwards, from person B before to person B afterwards. Just be on the lookout. Let's have a look at an example. In an experiment to test the effects of alcohol on the reaction times of people, a group of 10 students took part in the experiment. The students were asked to react to a light going on by pushing a switch that would switch the light back off again. Their reaction times were automatically recorded. After the students had each drunk 1 pint of beer, the experiment was repeated and the results are shown below. We're asked to do a 5% hypothesis test, and we're looking for whether or not consumption of a pint of beer increased the students' reaction times. So let's start this hypothesis. The null hypothesis, mu d equals 0, and the alternate hypothesis, we're looking to see if the reaction time has increased. So mu d is greater than 0. Let's just collect the variables, the important statistics that we're going to use. So sample size is 10, significance level is 5%, degrees of freedom are going to be 9, and that's enough for us to find our critical value. T-value of 9 degrees of freedom that is exceeded by 5%, that only has 5% above it. That t-value is going to be 1.833. Okay, so that's our critical value. We'll make a comparison with our test statistic, and then we'll decide if we have a significant result or not. So anything in the shaded region, any test statistic in the shaded region will be significant and will reject H0. Let's calculate the values we're going to need from here. So d bar, we should be able to find by summing all of the differences together. This can be typed straight into your calculator and you'll be able to get the answers. So putting all of these into list 1 on the summary screen, we can get 1.2 over 10, 0.12. The sample standard deviation is on that screen as well. That's going to be 0.1932. Okay, so from there, our test statistic, this time is going to be d bar minus mu d over s over root n. Just substitute those values in, let the calculator do the hard work, Just double check you have all the right values in all the right places. And our test statistic comes out as 1.964. Okay, well, is that significant? 1.964 is going to be in the shaded region. This is going to be a significant result. We have enough evidence to reject H0. Let's just do this formally. So we'll do our numerical comparison. So 1.964 is greater than 1.833. Significant result. And then our two conclusions, one mathematical and then one in the context of the question. So mathematical conclusion would say that there is evidence to reject H0, and the contextual conclusion, there's evidence that consuming a pint of beer does increase the students' reaction times. Okay, let's have a look at one more example. In this question, in this context, we're told in order to compare two methods of measuring the hardness of metals, readings were taken with both of the methods for 8 different metal specimens. So the result is shown in the table, and we're specifically asked to use the paired t-test, 5% significance level, to test whether or not there is a difference between the readings given by those two methods. Okay, so the t-test here is going to need us to calculate the differences. So that'll be the first thing that I do. For each of these pairs of readings, what is the difference between method A and method B? In this context, it wasn't quite a before and an after, but these are linked because they're the same metal sample and two different distinct methods being used on each specimen. Okay, let's go ahead and get started. So the null hypothesis is that the differences are going to have a mean of 0, so the mean of the differences is 0. And the alternate hypothesis is that it's not 0. We don't know which way around it's going to go, but we're looking to see if there is a difference. Sample size is 8, degrees of freedom is going to be 7, and the significance level, 5%, needs to be divided by 2, and that gets us 0.025. Okay, our critical value we can find straight from here. We're going to look up in the tables for a t-score, a t-value, 7 degrees of freedom exceeded by only 2.5%, and that gets us 2.365. Okay, let's get that on a diagram. It's a two-tailed test, so I'm going to label this at both tails, 2.365, negative 2.365. Any test statistic in that shaded region, we're going to reject H0. So here's the differences, 2, negative 1, 1, 3, 2, 0, 1, and 1. From here, we should be able to calculate our summary statistics to calculate the test statistic. Okay, firstly, what's the sum of D? We'll just add those up, we get 9. This can just be put into our calculator, list 1 and list 2. List 1 will have the differences, list 2 is going to have 1s. So, sum of D is 9, D bar is going to be 9 over 8. The sample standard deviation, this is on that summary screen as well, but to show exactly how we'll get there, we're going to use this formula, n over n minus 1, sum of d squared over n, minus the mean squared, and we'll sub all those bits in. So that gives us 8 over 7, 21 over 8, 9 over 8. All of this into our calculator, or like I said, from the summary screen, gets us 1.2464. Well, that's just the standard deviation. Let's go ahead and calculate our test statistic. So t is going to be d bar minus mu over s over root n. Substitute these values in. We get 9 over 8 all over 1.2464 over root 8. Okay, substituting. Let the calculator do its magic. We get 2.5529. Okay, is this a significant result? We're going to compare it to the critical value that we had, and this is in the critical region. We have a significant result. Let's summarize this as we usually do. So a numerical comparison. So 2.5529 is greater than 2.365. That's significant. And we get our two conclusions that we usually do, one mathematical and one in context. So, yes, we have enough evidence to reject H0. Additionally, yes, we do have a difference between the hardness readings given by the two methods.